I added up all of my possible rectangles that I could have, and made them infinite. So say I want to find the area not only under, but below, between the curve and the x-axis. And I make a bunch of rectangles. Let's see if I can use my straight line tool to do that. Okay, so here's one rectangle, and they don't all have to be left or right end point rectangles. They could be midpoint rectangles. So I could have another rectangle kind of going like this. Like I want to use the picture. I could have a fat rectangle over here, like this. I could have a skinny, I could have an upside down rectangle over here. That's not a, that would be bad. That's a bad rectangle. So, it's not a, that's not even a rectangle. Oh, I've got a good idea. I could actually make rectangles.
Wow.
So, where's my rectangle tool? Let's see if this works. So if I take this ooh, look at this. Okay, that's not very good rectangle. Anyway, oh, not too bad. Here's another rectangle. And if I added up all these rectangles, some are skinny, some are fat, some are midpoint, some are not. And that's kind of a midpoint rectangle. One more over to here. Let's go like that. So if I added up all of those rectangles, and I would get a certain estimate for the area between the curves. If you go below the curve, this will give you like a negative number, because you're multiplying negative y value times x value. The area is still positive. So you'll, in a little bit, I'll give you a theorem to find that the area under the curve, if the curve is all positive, then the area is positive. But if the curve is underneath the x-axis, then you take the negative of whatever the definite integral is to find the area of that curve.
Absolute value.
Okay? You just take the absolute value. Yeah, or you make the area because you'll get a negative number. You make that negative number negative, and you end up getting a positive number. Okay? So I bring up some stuff from the book to talk about because because I had it on a. So the so if I want to find the integral, or I want to estimate the area under the curve, I could I start at point A, x to 0 equals A, and x sub n equals b, and then I can add up a bunch of rectangles. These letters, it's kind of confusing because they have x's and c's all kind of mixed up together. Let me get rid of this thing somewhere. Sorry about all the mess on my paper. Okay, so c sub k, c is the point within this interval. So an interval from here to here is called delta x. So you have tons of little delta x's that you're adding up. So one interval, so here's delta x sub, or delta x sub, there's one delta x from here to here. There's another delta x from here to here. These are the points. So in this case, so notice in this case, they're using a left endpoint rectangle, aren't they? It looks like, and then in this point, they're using a midpoint rectangle. You see that? And over here, they're using it doesn't even say. Over here, they're using a midpoint rectangle. Over here, they're using a midpoint rectangle as well. So C stands for the value in that interval that you're using to compute the height of that rectangle. X, the subsequent x's, so x of k minus 1 and x of k, those determine the endpoint of one rectangle. And what happens is it doesn't matter where you choose to start and end those x's. If you take the limit of them, as n goes to infinity, you end up with the exact area under the curve, and that's what a Riemann sum is. So this is Raymond, he's some guy. So, anyway, let me go back to the book and see if I can show you some other stuff here. So a Riemann sum is given by this formula, right here. And this is a sum. This is not the integral yet. So S of n means sum. You know the sigma symbol? What does that sigma symbol mean? What it is, this means add them all up, okay? So this means add up all the rectangles from k equals 1, from the very first rectangle to the very last rectangle. It doesn't mean like x1, x2, x3. It just means the number of rectangles, or k is the first rectangle, n is the last rectangle. F of c sub k, this c sub k, that's the height, that's the x value, just so you know what you're looking at, that's the x value of the height of the rectangle. And f of c of k is the actual height of one of those rectangles. And delta xk, that's the width of one interval, right? And this thing means sum them all up, add them all up. So this is the definition of a Riemann sum. It's adding up a bunch of rectangles. Yes, sir?
Are all the
Not in this case. Not in this case. So you could, and like I said, I think yesterday is unlike it's going to be a disjointed lecture. That's okay. So the existence theorem says that all continuous functions are integrable, which means you can take the integral of them. That is, if a function is continuous on interval a to b, then the definite integral over a to b exists. Okay? So it just needs to be, it doesn't need to be differentiable, so you could have cusps in it, you could have flat spots in it, you could have places that, so that's continuous as well, right? But you could have a function like this, and that function would have an integral. Alright? So that's what that means. Now we're going to get into the integral symbol itself. And so, next thing.
Mr. Leader?
Yes, sir?
Is every function, like continuous function, integrable?
Yeah, that's what that just said.
Oh.
Good. So, okay. So, this is the more common way of writing that other formula. This is slightly different than that other formula that I just gave you, okay? And with this one, instead of the width of the rectangle going to 0, the number of rectangles goes to infinity. What happens to the width of rectangles as the number of rectangles goes to infinity? They get infinitely small. Okay? And this also says the definite integral of a continuous function on AB, let f be a continuous function on AB be partitioned into m subintervals of equal length. So in this case, the intervals are equally spaced. But it doesn't matter because I'm taking the limit of those as n goes to infinity, and those equally spaces essentially become nothing, and I end up with this. And this thing is also known as the integral. Okay? Another way to write the integral. Okay. Yes, I know that you know how to do it on your calculator. All right. That's very clever, but this will do you absolutely no good on the homework day yet. Okay? So, if you don't know how to do this without a calculator, you're kind of messed up. Alright? So, limit from A to B of f of x dx. Yes, this is the definite integral. So this is equal, this is the definition, more or less, of this. Alright? When you're doing an integral, this is called, this has a name, this is called the integrand. Just so you know what they're talking about. This is the same as what it was called in the in the differentiation chapter. This is called the differential. Good. This thing is called an integral symbol. Notice that it looks kind of like this, except it's smooth. Why do you think it looks kind of like that, except it's smooth? What it's, because it's a sum, but this is kind of, and it's not really kind of arbitrary that they chose that. So here you're adding up discrete numbers, right? You're adding up this rectangle plus this rectangle plus this rectangle plus this rectangle. As that sum goes to infinity, this curve becomes smooth because you're finding the exact area under a smooth curve. Yes, sir?
Would it be possible to make that bigger?
This?
The equation.
This thing?
Yeah.
Do you need to get a tub or a bottle?
Just, then I have to put it over my writing. I don't know. Is that better? Okay. Oh, I can still write them. Maybe you could. There, you can see it, right?
Yeah.
So this, and these things here are called the limits. This is called the lower limit of integration. Lower limit. And this is called the upper limit.
We need another definition.
Yeah, you should know what they're called, because they'll refer to them in the book, and you have to know what they are. Okay? So, be careful in a bit. These things can have different names. They can have, instead of calling the limit from A to B of f of x dx, they might ask you to find the limit from A to B of, I don't know, f of m dm, or they'll just use different variables in here, but don't be confused just because they do that. Alright? So then, you'll see the problems like this. They'll say, I'm going to get back to my, where'd this go? I'm not going to write down this whole problem because it'll take too long. So there you go. Integrand. They call this the variable of integration. X is the variable of integration. This piece here is called the differential. Okay? Integral of f from A to B. Lower limit, upper limit. Sometimes they call this the bound, and this is called an integral sign. And all right. So now, what if I have a problem like this, which you will? So I want to do this one, and all this is rewriting. Can you see this now? The interval from -1 to 3 is partitioned into n subintervals with length delta x equals 4 over n. Let n sub k denote the midpoint of the k subinterval expressed the length. This sounds very complicated, doesn't it? Okay. All this says is rewrite this as an integral. Okay. So this is the integral since you're going from negative. So what this means, is you have some function and you want to add up. It doesn't tell you how many rectangles to use. This is the distance from -1 to 3. It's not how many rectangles you have. So here's -1, here's 3, and you have some function, and we'll see what that function looks like in a minute. And so what you want to do is you want to go from -1 up to 3, and you just plug into, this just makes an equation. So I could take midpoint rectangles and plug them into this formula where this is the height of the rectangle and this is the width of the rectangle. Or I could write this as the integral of 3x squared minus 2x plus 5 dx. Okay? And that's all that's how you rewrite it. That's all there is to it. What is MK? That's the midpoint of one of the rectangles. So if this is a rectangle right here, that you're finding the area of, okay? MK is this the point, the midpoint of that particular rectangle. Okay? But it doesn't matter whether you're doing midpoints or left endpoints or right endpoints, because when you take the integral, you're taking the limit as this distance from here to here goes to 0, right? So the left endpoint and the midpoint are going to end up being the same. Okay? So when you take the integral, it doesn't matter whether you do midpoint rectangles or left endpoint rectangles or right endpoint rectangles. Notice that these are similar as they were in the last chapter, but not the same. Okay? Delta x is something that you could actually put a value on. Okay? So you could say, I want the width of my interval to be 0.5, or I want the width of my interval to be 0.1, or I want the interval to be 0.2, or something. But dx is still there by convention because it shows you that the y values here represent the height of those. This represents the height of all those rectangles, and this represents the width of all those rectangles, even though it's infinitely small width, you know. So that just
So I don't understand what information that second.
Let's do some specific examples. Could you stop, please, with your pen? Good. Get f of x. That should say this. If f of x is non-negative on AD, which means in an interval, should be little a, little b, then represents the area between f of x so it's just kind of another, physically, what this thing represents is the area beneath the curve if it's above the curve. So if you have some function and it's going like this, here's another arbitrary function that I drew, okay? So the integral from a to b, in this case, if this is f of x, dx, f of x dx is equal to the area underneath this curve. So that's equal to that area. You get that? Because if I summed up infinitely many rectangles, that's what I would get. Now, the reason it says non-negative, and not positive is because it can also be equal to 0. Like you could have a function that goes down here, touches the graph, bounces back up, right? And so if you had something like this, a curve that looks like that, the integral from a to b would still be the area under the curve, even though at one point that function touches the x-axis. Alright? Yes? Hello? Hello. Okay. Okay, the next part of that says, without me, I'll just bring it here so I don't have to write it again. Okay? I think I'm just tired and my voice is going. area under the curve, there's area under the curve. And the second part of that says that if the area is underneath the curve, okay, if f of x is negative, okay, or equal to 0, then the negative of that integral is the area under that curve. So, for instance, some cases you'll have a function that looks like this, and I want the integral from a to b, and I want this area. Well, the value that I calculate by adding up f of x is negative. You see that f of x is going to return a negative value in this case. So if I plug in 2 in here, maybe I get out negative 5. So this is the point 2, negative 5. And if I use that as the width of a rectangle, even though that rectangle is infinitely skinny, or if I use the negative 5 as the height of the rectangle, I'm going to end up with a negative number, right? So if you have an area, if you take the integral of something under the curve, you're going to get a negative number. To find the area under that curve, you make that negative. Yes? Okay? So now we could do some real life examples. That's what you've been waiting for, right? So,
A little break first.
a little break first. No. I want to get through it, okay? You had to break your first half-hour class when you weren't here. So, right? Right? Yeah. So, that's enough break time. So, anyway, so if I know that the integral, and some of you know how to do this already, the integral from 0 to pi of sine of x dx. I'm going to learn how to do this in like 2 sections. So I know that some of you, Mr. Lowe told us how to do this, I know how to do it already. That's okay, but that's not what we're doing, okay, in this chapter. So if I know that this integral is equal to 2, in other words, if I have this area under the curve from 0 to pi, right? This area, if this is sine of x, goes like this, right? And it goes like this down here, right? So if this is y equals sine of x, I know I can do integration techniques and figure out that that area is exactly equal to 2, which you'll learn how to do when you're in front of me up there. Okay? What would the integral, so this is where your calculator's not going to help you, okay? What would the integral from negative pi to pi of sine of x dx, what would that be?
Would it be here or?
Draw a picture. Okay, this goes from negative pi to pi. So if I add this piece plus this piece together, what am I going to get out? 0. Okay? Because this is considered, this would be a negative integral. The area of that piece is 2, but the integral is negative. Okay? Because the y value is a negative, so you're going to get a negative value if you were to plug this into your calculator. Okay? You could show that too. So if you take your calculator, I was going to wait till tomorrow to show you this, but if you were to take your calculator, come on, buddy. All right. And I go, I want to change the view, always in front, and I go y equals sine of x, sine of x, close the parentheses, get rid of everything else, and I'm going to make sure I'm in radian mode. I'm going to do a zoom trig, I think, zoom trig 7.
What's zoom trig do?
I think it just says it's from negative negative 2 pi to positive 2 pi, okay? And I can do a second calculate, and I can do the integral, okay, of f of x dx, like this, okay? And I'll say the lower bound. So I want my lower bound, I think I could just plug it in here. Negative second pi, okay? And then it'll say upper bound, and I go second pi, like that. And I hit enter. There you go. The integral is equal to 0. Okay? But you're only allowed to do that in cases where the integral is ugly. Okay? And you're not going to know how to do it by hand. So I'm just showing you how to do it. But notice that it's shaded in this part, shaded in this part. This is considered a negative. If you plugged in negative pi to 0, you would get negative 2. If you went from 0 to pi, you would get positive 2. If you add those two things together, you get out 0. Okay? So now I am going to give you kind of a little break. I'm going to let you work on an investigation on page, and this should only take you 10 minutes, and I am going to collect it. On page 283, what page? 283. I already did one of the problems for you, but page 283 to exploration 1. It's just one exploration 1.
Can you bring it up?
Okay. What? No, you could use your book. It's coming up. You could work on it with a partner too. You can work on it with a partner. Okay. Again, so the integral of a constant is equal to the constant times the width of the interval. And so, does that make sense? It makes sense for us. And so, the integral of a constant function is equal to the width of the interval. So this is the width, right? And this is the height of that constant function. So for instance, if I want to go from a equals 2 to b equals 7, right? So if I don't want to find the integral from 2 to 7 of the function y equals 3, right? This represents the function y equals 3, right? So that integral is just the area under this curve, which is 7 minus 2 means the width is 5, right? And the height is always what? 3, okay? And so that is going to be equal to 3 times 7 minus 2, which is 5, which is 15. And that's physically what that means, okay? The area under that curve means you're finding this area. So the integral, so if I said, what's the integral from negative 2 to 3 of pi dx? Well, what would that be? Yes, sir.
Why doesn't it dx go to
Because f of c, because c means, it doesn't mean that the value is c, the value is a constant, okay? So, I guess, yeah, it's just because it's a function of x, where the x is always, or y is always equal to 3. Alright? What would this be? 5 pi?
5 pi?
Very good. Alright, any questions on that? That's easy. Alright, I just want to do a couple more little examples that you might see. So say you were to see something that looks like this, and they say find the integral without your so this is like, you're supposed to do it graphically, not with a calculator. Say they want you to do the integral from negative 3 to 3 of the square root of 9 minus x squared dx. And you say, I have no idea how to do that. It's 0. No. Not 0. Because that's only 0 if it's an odd function, right? If it's a sine wave. It's not 0 for any function. What does this function look like? Yes, sir.
Semicircle?
Very good. That's a semicircle. So sometimes you have to recognize this, right? This is y equals the square root of 9 minus x squared, which if I square both sides, I get y squared equals 9 minus x squared. And if I bring this over here, I get x squared plus y squared equals 9. And so this is a semicircle with a radius of what? 3. Okay? So what you're finding is the area of this semicircle right here. What's the formula for an area of a semicircle? Or what's the formula for an area of a circle? So this would just be pi times 3 squared divided by 2. Or 9 pi. No, that's the same. You have to, right? Yeah, I know. 9 pi over 2 would be your answer. Okay? So that's kind of tricky a little bit. Okay? All right. You will also see ones that look like this. And these you're not supposed, that last one, when you'd have to use, like trig substitution or something like that to solve it algebraically. So those of you who know how to take the antiderivative and then use the fundamental theorem, which we'll learn in 2 days, you can't do that on that one because you don't know how to integrate that yet. Okay, so, and you'll learn that kind of integration later. But what if I have this? You don't know what I'm talking about. The integral from negative 1, no, let's not go from negative. From 2 to 5 of x dx. Could you do that? What does this look like? This is y equals x, right? Because this is y equals, this is the y value, so y equals x, which looks like what kind of line? A line with a slope of 1, right? And so what you're asked to find here is the area under the curve of this straight line from x equals 2 up to x, not a curve, it's a line, but you're trying to find this area right there. How could I do that?
Well, maybe rectangle.
You
You can do it square, yeah, you can do it a number of different ways. You can divide it up, you can find it as a trapezoid. You remember trapezoid? What would this point, what's this point right here? 2, what's this point right here? So this is point 2, 2, this is point 2, 5, right? So, remember the formula, 5, 5. This distance is what? 3, right? So you can find the area of this trapezoid by remember you learned this in geometry?
Oh, God.
Area of a trapezoid, base 1 plus base 2 times the height divided by 2. What's that area equal to? What's base 1?
3.
No, this is a sideways trapezoid.
5.
Base 1 is 5,
2.
base 2 is 2, divided by 2, what's the height of this trapezoid? 3. That's 10, 5, 15. The answer is always 15, no matter what number. Okay. The other thing, what if I integrated this from negative 1 up to 5? What's going to be true about this area here? It's a so you would have to find the area of this negative triangle, and then you would have to find the area of this triangle, and then add those two areas together, where this one is negative and this one is positive.
It's
not 15? Sorry for those of you out in TV land, I made a mistake. 7 times 3 is 21 divided by 2 is 10.5. Sorry. Okay.